Thank you very much. Maybe it's all right to be there. Yeah. Okay. So my name is Andrea Piccolroaz, quite difficult spelling. I'm from the University of Trento in Italy. My background is civil engineering, so I don't know how many of you are civil engineers. Today I'm going to talk about material instabilities and architected materials. My research interests are in solid mechanics and structural mechanics, and I am interested in how materials fail. So one possible approach is functional mechanics, but another approach is material instabilities. So why to study material instabilities? As I just said, because material instabilities are usually precursor of the failure of a material. So here you see an example of a cylindrical sample which is loaded with simple compression. And initially, the deformation is uniform, but at some point of loading, a shear band appears. And this later becomes a crack and brings the material to failure. So it's very important to understand material instabilities and be able to predict the condition where material instabilities can occur. Okay, so this is the outline of my talk. Is divided into two parts. In the first part, I will give an introduction to material instabilities in continuum mechanics, for who is not familiar with the subject. So I will give the definition of a stable material in the Mandel sense. And on the basis of this definition, I will give a classification of material instabilities. And then I will introduce the perturbative approach. In the second part of my talk, I will try to make a link between solids and architected materials. And I will show the homogenization schemes in both statics and dynamics. And I will try to answer this question. Does homogenization work in case of material instabilities? And we will see that we need to distinguish between macro instabilities and micro instabilities. There is another type of instability, which is called flutter, but I don't think we have time to cover this today. So let me start with the introduction to material instabilities, and I will begin with the description of incremental waves in prestressed hyperelastic solid. So in this slide, you see the incremental equation of motion and the incremental constitutive law. So here S is the first Kirchhoff stress, and L is the gradient of incremental displacement. So I would like to point out here that since the solid is prestressed, the governing equations must be formulated in the framework of the incremental theory of nonlinear elasticity. So the constitutive C here is the tangent constitutive operator, and in case of a prestressed hyperelastic solid, the most general form of C is given by this formula. So it's the sum of two terms. The first term is the material part, depending on the elastic properties of the solid. And the second term is the geometric part, which is produced by the prestress in the solid. Okay, so here is the prestress and is the factor which induces material instabilities in the solid. Indeed, E is always positive definite, or at least we assume it's always positive definite, but the second term is indefinite, so can produce loss of PD of the tangent constitutive operator.
You want to explain the symbol there, but show what that means.
This symbol is a tensor product, a specific tensor product.
It only has a circle, doesn't it?
Usually it's a circle, but this is a bit different because
C is the fourth order tensor.
yes, this is a fourth order tensor.
You do a point, right?
So I see a second order tensor, I see a fourth order tensor. I remember well, this is the definition of this operator. Okay, so So that you should imagine that you are loading your material. So this is press, and this is displacement. You're loading the material up to the nonlinear regime, and then you stop at some point here. And this define prestressed configuration, and then we consider small increments from this prestressed configuration.
Just the tangent, right?
Yes. And the tangent is, yeah. This tangent is the tangent constitutive operator. Okay, now consider a plane wave in a prestressed elastic solid in a standard form where k is the wave vector, the scalar k is the wave number, n is a unit vector, the propagation of direction of the wave, omega the angular frequency, and c omega over k is the wave speed. So from the governing equations, incremental governing equation, you obtain the usual eigenvalue problem governing acoustic waves in a solid. So here this matrix A, tensor A, a function of n is the so-called acoustic tensor. Okay, and the acoustic tensor is related to the tangent constitutive operator through this equation here, and is clearly seen from the eigenvalue problem that the eigenvalues of the acoustic tensors are the wave speed squared, and the eigenvectors G are the wave amplitudes or polarizations of the wave, so that if G is parallel to n, we have pressure wave, and if G is orthogonal to n, we have a shear wave. So now we are in a position to give the definition of a stable material. There are many definitions of stable material. This is one possible definition given by Mandel in 1966. It says that the material is stable as long as waves can propagate in the solid in any direction with a finite non-vanishing speed. So this condition is satisfied when the eigenvalues of the acoustic tensor are real and strictly positive. So this is known as strong ellipticity condition. So as long as the solid is strongly elliptic, is stable, and material instabilities are excluded. So now we, on the basis of this definition, we can give a classification of material instabilities in elastic solid, and this is related to the symmetry properties of the tangent constitutive operator, actually, the symmetry properties of the acoustic tensor, and therefore of the tangent constitutive operator. If C is symmetric, and this is the case for of hyperelastic material or associative elastic material, then also the acoustic tensor is symmetric. And in this case, loss of ellipticity is when one eigenvalue becomes zero. And this is known to be related to strain localization and shear balance. If C is non-symmetric, and this is the case of non-hyperelastic materials or non-associative elastic materials, then A is non-symmetric, and loss of ellipticity may occur when two eigenvalues becomes complex conjugate. And this is known to be related to flutter instability, which is an amplification, exponential amplification of amplitudes of waves propagating in the solid.
So theory, the first one, but it's predicting angle.
Yes, the angle of shear bands, yes, is related to the direction n. Actually, n is normal to the shear band.
Flutter is called flutter.
I think in analogy with flutter in higher elasticity. Because this flutter in higher elasticity is well known, but flutter instability in a solid is not so well known. Was the existence of this instability in a solid was postulated by Rice in 1977, but was never experimentally detected. So there are some. Sorry?
By this choice of word, whoever chose the first level context. So what does word flutter mean in common non-mathematical, non-mechanical language? Why it was chosen for this context?
This one in solid mechanics, yeah. I think because it's similar to the flutter in an aeroplane, for instance, when the wing starts to vibrate and the amplitudes increase in time. In this case, you have exponentially growing space, but it's a similar phenomenon. Okay, so what happens is this. So this is the complex plane. So if C and A are symmetric, then they live on the real axis, the eigenvalues. So those ellipticity is when the smallest becomes 0. Okay, this is the first case. But if C and A are non-symmetric, then what happens is that two eigenvalues merge together, and then they split in the complex plane, becoming complex conjugate pair. And this is flutter instability, which is also known as Hopf bifurcation in the context of dynamical systems. So I now will illustrate the perturbative approach to material instabilities, which is one of the most effective method to analyze these instabilities in a solid. And I will illustrate this method to a simple example. This is a mechanical test done on a cellular material, which is loaded in uniaxial strain conditions. And you see here the stress strain curve. So the threshold of instability is the point of maximum of the code, so it's point C. But if you look at the figures, especially this one, you see that at the point C, the material looks still homogeneous. There are no signs of instability, strain localization, or shear bands. So the question is, can we decide that C is on the verge of instability without loading to E? And the answer is yes, use the perturbative approach. So this is illustrated here in this slide, where you see the experiment, and this figure is a point C on the verge of instability, so the material is still homogeneous, but then apply a small perturbation in the form of a point force at the center of the sample. So actually, what we do, we just put a small weight at the center here of the sample, and immediately shear bands appear. So this perturbation or perturbative method is very effective in detecting the threshold of the material instabilities. And since the perturbation is a point force, to apply this method, we need the Green's function. And some years ago, actually during my PhD, I derived together with John Willis and my supervisor, Davide Bigoni, the Green dynamic time harmonic Green's function for a general material with non-symmetric constitutive operator. And this Green's function is crucial to analyze flutter instability in a solid. So let me now move to the second part of my talk. I will now link solids and architectural materials to the homogenization theory. And I will try to answer this question: does homogenization work in case of material instabilities? So the idea is to design artificial materials in the form of periodic lattices of elastic beams, which are axially preloaded to some extent, and then superimpose incremental deformations and analyze the response of the lattice in order to identify possible instabilities and try to connect these instabilities in the lattice with the material instabilities in the equivalent solid. Okay. So for this, we need to formulate the governing equation for the lattice. So we need the time harmonic dynamics of prestressed rods. And here we use the Rayleigh beam model, which is the standard Euler-Bernoulli model enhanced with a rotational image. And this, according to the incremental theory of nonlinear elasticity, these are the linearized equations around a prestressed configuration. So the beam is prestressed, axially prestressed, and then we superimpose these incremental deformations. And the first equation is governing axial weights, and the second equation is governing flexural weights. And since these are just linear ODEs, can be solved exactly, and the solution can be written in this convenient matrix form. So this displacement field U is given by a matrix of shape functions times a vector Q collecting displacement and rotations at the end of the term. I would like to emphasize here that although this looks similar to the finite element method, this is not a finite element approximation, is an exact solution. And indeed, the shape functions depends on both the angular frequency and the prestressed speed. In the standard finite element method, the shape functions are independent of the frequency, and independent of the prestress, usually are just Hermitian cubic polynomials.
Two dimensional there.
Yes, this is two dimension. Yes, but it can be straightforward 3D lattices. Rayleigh beam model.
This looks quite similar to Timoshenko, right? Model when it has this stretch and then
yes, the Rayleigh beam model is there's a model in between Euler-Bernoulli and Timoshenko because it has additionally to the Euler-Bernoulli beam, it has the rotational inertia term, but still assumes unshearability. In Timoshenko beam, you also account for shear deformations. So it's more enhanced. Okay, to derive the governing equation for the entire lattice, we can use a variational approach. So you see here the energies for a prestressed rod, the kinetic energy, the elastic energy, and the potential energies of the prestressed beam. And all these energies can be written in a matrix form, as you see, where M is the mass matrix, Kn is the material stiffness matrix, and Kg is the geometric stiffness matrix. And again, this is not a finite element approximation. It looks similar, but these are exact matrices derived from the exact solution. This is to show how the prestress dependent stiffness matrix looks like, and actually this is the static case, so for zero frequency. And for the dynamic case is even more complicated. But you see here the presence of the prestress in these functions P1 and P2, which are functions of the axial prestress in the beams. So the governing equation for unit cells are derived with standard arguments. So we take the Lagrangian function for the unit cell by summing the energies for all the beams inside the unit cell. And then with the standard machinery, we derive the governing equations and we apply the time analytic function. So the governing equation reduced to this form A Q equal F, where F these are external forces on the unit cell. And the matrix A is minus omega squared N plus K. The last step is apply blockade conditions on opposite side of the unit cell, so that the unit cell is representative of an infinite lattice. And this is done through this matrix Z, which is function of the block vector K. So applying the blockade conditions, the governing equation reduced to this eigenvalue problem, A star Q star equal to 0, where A star is an Hermitian matrix governing block flotte waves in the lattice. So from this is immediate to obtain the dispersion relation, because this eigenvalue problem admits non-trivial solution only when the determinant of A star is equal to 0. So this is the implicit formula, that is the dispersion relation for the lattice. And this can be plotted, for instance, with Mathematica. So these are dispersion surfaces. This is an example of dispersion surfaces for a square lattice, and you see here a comparison between the Euler-Bernoulli beam model and the Rayleigh beam model for two different slenderness of the beams. And from this figure, you see the effect of the rotational inertia, which is negligible at low frequency. So at low frequency, Euler-Bernoulli and Rayleigh gives more or less the same dispersion surfaces, but the effect of rotational inertia is important at higher frequencies. This maybe is more evident from the band diagrams, which are plotted here for the first three zone. Here, blue lines are for the Euler-Bernoulli beams and red lines for Rayleigh beams. And you see that effects of rotational inertia is a lowering of the bands for any frequency. But this is more evident at high frequency. At low frequency, you see the course practically the same. And this is another example of dispersion surfaces. So by playing with the lattice parameters, you can obtain several interesting effects, like a completely flat band at a specific frequency. So if you fix the slenderness of the beams to this value, you have this completely flat band, which corresponds to an infinite set of standing waves, and also multiple Dirac cones for a rectangular lattice, so changing the aspect ratio of the lattice. Now, let me move on to the homogenization. So we will try to create this link between the architectural materials and the effective continuum. So we start from lattice in a stress-free configuration, then we apply axial load. So we obtain this prestressed configuration, current configuration, and we superimpose the incremental deformations. So we want to homogenize the incremental response of the lattice. Okay. So the lattice is partially periodic. So the entire lattice can be obtained by repetition of a unit cell along with two vectors A1, A2, which are the direct basis of the lattice. And in dynamics, the periodicity is enforced using the Bloch theorem. So the incremental displacement field is quasi-periodic. And this exponential term is the Bloch shift, where K is the Bloch vector. In statics, periodicity is enforced using the Cauchy-Born hypothesis. So the nodal displacement of the lattice are given by the sum of two terms. The first term with tilde is a periodic term, and the second term is a homogeneous term, which is related to the macroscopic deformation of the equivalent continuum. So L is a macroscopic deformation of the equivalent solid, which is assumed uniform in the solid. So the homogenization schemes are completely different in statics and in dynamics. In statics, you obtain the homogenization by matching of the incremental strain energy densities up to the second order. So you see here the incremental strain energy density of the equivalent continuum up to the second order. The first term is the first order work produced by the prestressed, and the second term is the second order work produced by the increment of the first hierarchy of stress. So by matching first and second order, we can obtain the effective properties of the continuum. So by matching at first order, so matching the first order work of the continuum and the lattice, we obtain an analytic expression of the prestress in the equivalent solid as a function of all material parameters and axial prestresses. And by matching at second order, so the second order work between continuum and lattice, we obtain an analytic expression for the tangent constitutive operator. Again, as a function of all lattice parameters and axial prestresses. This is known as micromechanical condition or Hill-Mandel theorem. In dynamics, the homogenization scheme is completely different. It's based on a match on asymptotics of the governing equation for block waves in the lattice. So this eigenvalue problem, A star Q star equal to 0. So we consider the low frequency long wavelength asymptotics of these equations when omega and K goes to 0. So we expand both A star and Q star and we replace it in this equation, which is, since is an identity, must be satisfied at every order. So we obtain a sequence of linear systems that can be solved one after the other. And for the homogenization, you need to solve up to second order. So you need to solve the first three linear system. The first system is the homogeneous system, but the system matrix A star naught is singular. So this equation admits two independent solutions, which are the rigid body translations of the lattice in X and Y direction. The second system at first order is non-homogeneous, but the system matrix is still A star naught, so it's singular. So you have to impose a solvability condition on the constant term, and it can be proved that this system is always solvable and admits two independent solutions, which are approximations of the amplitudes or a polarization of the acoustic waves in the lattice. And the third system at second order, this is again a non-homogeneous system. This system matrix is still A star naught, so it's singular. So you have to impose a solvability condition on the constant term. The constant term must be orthogonal to the kernel of the system matrix. So it must be orthogonal to the two body translations. And these solvability conditions turn out to be in this form, which, as you can see, is equivalent to the eigenvalue problem governing acoustic waves in a solid. So this matrix AL, a function of N, is identified with the acoustic tensor of the equivalent solid. And then from the acoustic tensor, it's straightforward to obtain the tangent constitutive operator. So now I will try to answer the question, does homogenization work, with some examples. So for this, I consider a specific geometry of the lattice. So this is a slanted prestressed beam lattice reinforced with linear springs. So the blue lines are Rayleigh beams, and the thin dark lines are linear springs. So the lattice parameters are lambda1, slenderness of horizontal beams, lambda2, slenderness of inclined beams, kappa, the spring stiffness, and alpha, the angle of inclination. And additionally, we have the two axial prestresses, P1 in horizontal beams and P2 in the inclined beams. So this is the first result, is the prestressed tensor in the equivalent solid, determined at first order, and as you can see, is exact solution. So you have a symbolic formula giving the prestress in the effective continuum as a function of all lattice parameters and prestress in the beams. And this is the second result, is the tangent constitutive operator. Again, this is an exact solution. So you have a explicit symbolic formula for all the 10 components of the tangent constitutive operator as a function of all lattice parameters and prestress in the beams. And there are 10 components here because the lattice under consideration is completely anisotropic. So there are 10 independent components.
The mathematical is that out?
Yeah, this is everything was solved in mathematical symbolic. If you have enough time.
Well,
Yeah.
I mean, it's all connected in the universe.
Yeah, because exactly. Actually, what you do is you just solve linear systems here. Yeah. But of course, symbolically, it's not so simple because it could be huge. Okay, so yes, this is what's done in mathematics. So to answer the questions, does homogenization work? We need to distinguish between macro and micro instabilities. So this is the case of macro instability. A macro instability is a buckling or bifurcation of the lattice characterized by an infinite wavelength mode and can be detected on the dispersion surfaces by a vanishing slope of the acoustic branches at the origin along specific directions. So you see here the acoustic branches of the lattice, and prestress is increasing from left to right, from 0 up to value close to the loss of electricity. And you see these slopes at the origin, which becomes 0 along specific directions, which are linked to the inclination of shear bands. And it can be proved that a macro bifurcation in the lattice is equivalent to failure of electricity in the homogenized materials, which means that you will observe formation of shear bands in both the lattice and in the equivalent continuum. And this is where homogenization works. This is the case of a micro bifurcation. A micro bifurcation in the lattice is characterized by a finite wavelength mode and can be detected on the dispersion surfaces by a zero frequency wave with a non-null wave vector. So again, the prestress is increasing from left to right, and you see these points, red points here, when the prestress is close to the micro instability. This corresponds to waves at zero frequencies, but non-null wave vectors. So these are micro instabilities in the lattice. And a micro instability in the lattice remains completely undetected in the homogenized material. So the lattice is unstable, but its equivalent continuum is still stable in the elliptic regime. So depending on the lattice parameters, the first instability to occur can be macro on micro. So you see here uniqueness or stability domains for both lattice and its equivalent continuum for two cases. Here, the loss of electricity in the effective continuum is denoted by a solid line, whereas the spots denote instability in the lattice. So in the figure on the right, this is for a square lattice without spring reinforcement, and on the right is the case of square lattice with spring reinforcement. So in the first case, you see that the first instability to occur in the lattice is always a macro instability for all combinations of prestress P1, P2 in the beams, so that stability domains of the lattice and of the solid coincide. But in the second case, you see that for some combinations of the prestress in the beams, the first instability in the lattice is a micro instability. For instance, if you follow this equibiaxial path, the first instability that you encounter is this, which is a micro instability. So here the lattice becomes unstable, but the solid, the equivalent solid, is still stable in the elliptic regime. So this is where homogenization does not work. So to validate these findings, we apply the perturbative approach to shear bands, so using the Green's function. And here you see a comparison between the lattice in the upper part of the figure and the equivalent solid in the lower part of the figure to a perturbation, which is a force dipole applied near the center of this domain. The lattice response is simulated in finite elements in terms of Newton physics, and the response of the solid is just plotted by using the Green's function. And this is the case of macro instability, when the first instability in the lattice is a macro instability. So you see the prestress is increasing from left to right. And when you approach the instability value, you clearly see the formation of shear bands in both the lattice and the equivalent solid. And the match between the two is really impressive. This is where homogenization works. So the architected material shows shear bands occurring within the last range, and shear bands can be activated or inhibited with the prestress. And this is the case of micro bifurcation. Here I show only results for the lattice because the solid is still stable, so you see nothing in the equivalent solid, but here in the lattice, you see the effect of a micro bifurcation. So in this case, micro bifurcation is not localized, so it's not a shear band. So you have periodic mode extending all over the lattice. And this is invisible in the effective continuum. So to conclude, I report here again the outline of my talk, where I have included the answers to the question, does homogenization work? So as we have seen in this seminar, for macro instabilities, the answer is yes. For micro instabilities, the answer is no. And for flat instability, we didn't cover this in this seminar, but I can tell you that the answer is yes. So also for flat instability, the homogenization works. You can analyze also flat instability in the effective continuum. This finally are some references to this work. So if someone is interested, of course here also up to the end of the month, so we can discuss if someone is interested. Thank you for your attention.
Maybe I can ask the first question. When you're increasing the stress, you're showing the dispersion curves, the band surfaces. Larry was very happy with. The micro ones, instabilities that don't work with homogenization, those the ones, the tips that get dragged down.
Yes.
So they've got non-zero array wave numbers.
Non-zero.
Well, not vanishingly small.
Non-vanishing wave vector.
If you near the origin, where the lines are in, yeah, those points.
I mean, these points.
Yes, those are the ones that don't work.
Yeah.
Why is it okay to homogenize for those points?
No, here the homogenization does not work because homogenization you are matching the asymptotics at the origin. So you only see, so you don't see in the homogeneous solid, you don't see these solutions.
So those are not the ones that you show in subsequent slides.
This one, no?
No, names that. Yeah, this sort of stuff.
Yeah.
You're saying homogenization doesn't work. It's those points.
Yes, exactly. Yes.
But when you expect those to be ones which homogenization doesn't work straight from the surfaces, the location, you're away from the origin.
Yes, if you're away from the origin, solid, the equivalent solid doesn't see.
And that's what you're confirming here.
Yeah.
Okay. But you could have predicted.
So these spots here, these are micro bifurcations, so corresponds to this equation.
These points
here.
Away from the origin.
Yes. These are the micro instability.
So I'm just asking, from this alone, you could predict, can you predict that they won't work?
Yeah, yes. Okay. Because you see that at the origin here, the slope is always strictly positive. So the velocity, waves with velocities are always strictly positive for every direction. So the equivalent solid is strongly elliptic and stable. So the equivalent solid is stable here, but not the lattice.
what you're saying is that if you had that picture, then you would know the modular.
Yes,
Yes.
yes.
Oh,
that's-
from
yes.
the location within the bronze rather than the sling that occurs at those points. Nearly away from
Because, yeah,
the sense of the origin.
if I would plot here the acoustic surfaces for the equivalent solid, I would see just surfaces on this drawing. There is no such points. They are because it is the approximation of the origin. So it's quadratic form is a quadratic form. So
More questions?
Looking at me again.
No. Beyond you. As long as it isn't the question that we expect.
No, I think we started about so when I hear about homogenization, not like in my customer information, which homogenization, right? Classical homogenization may be working, but maybe some more advanced, non-classical versions of homogenization.
this is just the classical homogenization. So we derive the Cauchy equivalent solid.
That's what I did again.
If you got
My other preferred to connected to my other preferred topic, favorite possible. In the high contrast from classical homogenization, right? And so in context of this prestressed materials, right? If I think about a periodic structure which you start prestressing, right?
yes,
Then I can imagine that some components for one reason or another, right? Microscopically, right? Some components may start reaching the point of local loss of stability earlier than others, right? But
Yes.
The bulk still maintains some kind of strong ellipticity or how you call it, right? Stability. Some components within start kind of softening, right? You could say, right?
Yeah.
This curve, right? Local stress strain relation starts softening, but then translated to my other preferred language. This means that you're developing for this incremental story, right? You might see some components becoming incrementally much softer than the others, right?
yes,
And then it's done low, right? Okay. But this is a scenario for this micro kind of resonance, maybe another word for resonance, micro instability, right? Which sort of when you start doing a symbolic analysis, you have to release this two-scale analysis, right? To remind us how it works classically, right? But yeah, you have some kind of critical regime.
Yeah.
This guy start responding.
so you are talking about higher order.
The limit system is principally two-scale, right? And this, the response. Maybe it's about this kind of
No, you are talking about higher order.
this kind of local figure. I think just what I would translate it from kind of dynamics, right? Band gaps, dynamics to the source of stability, low frequency band gaps, right? Image near the local resonance. Maybe if I translate it, there will be some kind of loss of global stability, right? Caused by this.
Yes.
Effects.
Yeah, I think one open question is yeah, yes. I mean, one open question is we can homogenize at higher order, so obtain higher order continuum or non-local continuum that can catch this micro instability. This I think is an open question.
Any other questions? Ask another ones, might be tangential, but there was some discussion on Monday about these flat bands, where you showed one earlier for the lattice. And I heard, I think Sonia saying earlier in August. You have to go through me. Oh, right, okay.
Yeah.
So you can't get those flat bands in certain cases. So if you homogenize and go to a continuum, does that disappear?
Yes.
No.
I mean, I guess you do higher frequency homogenization. what I do is using low frequency, low wavelength to obtain the effect continue.
Yeah,
This disappears in the usage.
you get higher order stuff.
If you do higher frequency homogenization, but I never think cluster does the higher frequency homogenization.
You never get a flat band. Is that the discussion earlier in the week, or whether anyone else knows about this sort of stuff?
US,
the formulation of the panel, the system became a difference here, and there's a conveying required, but on the frequency will also be wave.
All we showed flat bands are in the week, but there was some discussion about the fact that they couldn't control flats. So it's
almost flat, right?
this is
this is pretty flat to me. But I think that's because it's a lattice, so when just put the continuum.
I mean, it's just a result of our computations. We
Just
plotted the spatial surface and we played with the slenderness and we found that for this value was flat band. But I think it's related to some natural frequencies of appeal. Simply supported in
my understanding of the conversation idea was he was correct, and it needs to be a lattice in order to get the back.
And there is a lattice.
Sorry, I was a bit of a tangent, but no one else was asking any questions. All right. If there are no more questions, last chance. Is that no? Okay, well, we thank Andrea again.